Hi guys, so in this video what we're going to do is we're going to introduce the concept of complex numbers. We'll then look at the Argand diagram and also the modulus. So to start with, what I want you to do is consider the quadratic formula there, x equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And what we're going to do is we're going to use that formula just to solve the equation below here, x squared plus 4x plus 12 is equal to 0. So that means that what we have here is 1 is equal to my a, we have b is equal to plus 4, we have c is equal to 12, and we're going to throw it into the formula just as we normally would. So minus b, so minus 4 plus or minus 4 all squared minus 4 by a, which is 1, by c, which is 12, square root him, and then what we have that is all over 2 by 1 on the bottom. Now, the interesting bit here, or the bit I'm interested in, or we're all interested in, is that square root here. So if we work out the rest of it, minus 4 plus or minus, and if you work out that square root, guys, you get minus 4 squared, which is equal to 16, and then we get minus 48 all over 2. Now, this bit here, this 16 minus 48 is where we have the problem. Because now what we're going to end up with is we're going to end up with a negative number within a square root. And if you try to put that into your calculator starts to not like it and gives you a maths error. So we have a bit of a problem. This has been a massive problem to mathematicians for a long time, and I think it was in the 16th century that Bombelli, an Italian mathematician, came up with the concept of what we now call the imaginary number. So what Bombelli said was that if you have the square root of negative 1, obviously we are unable to calculate this. As I said, if you stick it in your calculator, it doesn't like it. There is no real answer to this. He said what we're going to do is going to denote it as I for imaginary, which then led to the fact that I squared led to root minus 1 squared, which was just minus 1. Now, this meant that we could deal with a whole load of quadratic equations which gave us problems with the fact that we had the negative square root, and we could now actually solve them in what was called the complex or imaginary plane. So how do we actually solve the question we have above there? So let's just finish that off and we'll bring it down. So we've got minus 4 plus or minus there. 16 minus 48 I think is minus 32. So we've got the square root of minus 32. That's all over 2. And what we do here now is we change the root 32 or the root minus 32 and we break it up as I'm about to show you. So what we have is root minus 32 is exactly the same as root 32 multiplied by root minus 1. And that means now that I can work out root 32. Root 32 is a positive number, and I just change the root of minus 1 to I. So this now becomes I and root 32I. I can use my normal laws of surds to break that up if need be, but all I have to do now is just put the I after. So this now means I have minus 4 plus or minus, and the negative or the square root of the negative 32 changes to root 32 by I. The I tells us that we're in the imaginary plane, and that's still over 2, and then I can simplify that as needs be. But you can see here the only real difference in what we are doing to normally solving a quadratic that has no imaginary part is that if it's a negative 32, we're doing the square root of a negative 32, we just use our normal square root rules, i.e. square root of 32, and then all we do at the end is we whack on an I. So that leads nicely on to what is a complex number. Well, we can define a complex number. We usually use the letter Z, lads, so Z, and Z is equal to some A plus BI, where A is the real part, so the real part of the complex number you see here, we can just call that RE of Z, and B is the imaginary part of the complex number and is written IM Z. BI is called the imaginary term, just for clarification there. So some examples of that are, I'll give you a couple now, is that if I had Z was equal to 3 plus 4i, the 3 here is the real part of the complex number, the 4i is the imaginary part. If I give you another example and I say, okay, suppose I had z is equal to 4, that is still a complex number. It's a real number as well because it only contains the real part. It's essentially z is equal to 4 plus 0i here. So that's just a real number. Real numbers and imaginary numbers are subsets of complex numbers. So pretty much every number that you come across is a complex number. You just didn't know it yet. Let's have a look at example 1 here. We'll just quickly go through, state the real part and the imaginary part of each of the following. Guys, this is really straightforward. If it hasn't got an I on it, that's the real. If it has an I on it, so the minus 3i, that's your imaginary. Same here. That's your real. That's your imaginary. That there has no real because there's no real number. There's no number without an I, so that's just an imaginary number. And here z is equal to 9, the last one. You can see here that there is a real number. There is no I after it. So it's not difficult to work out which part of a complex number is real and which part is imaginary. Now, they sometimes like to ask you to simplify i's here, so I'm going to talk about i's and hopefully we can come up with a rule that for any I to the power of anything we can work it out, even at 251, which at the moment seems quite difficult, but I'll show you a very easy way to do this. So the major definition we have here, the major definition we're going to use is we know that I squared is equal to minus 1. Remember, we made that definition on the first slide here. So using that information, hopefully you can see that if I do I squared by a square, that's equal to I to the power of 4. And that means that what I'm going to get here is minus 1 squared is equal to I to the power of 4. And minus 1 squared is just 1 is equal to I to the power of 4. Now, if you learn those two relationships between I and the real number there, 1 and minus 1, you can't really go too wrong here, because all we're going to do is going to break up the i's using our index laws into I squares and I to the 4th. So what do I mean by that? Well, let's have a look at the first one. So we have I there is equal, so we've got I cubed. Now guys, what you should know, or you should definitely know this, is I cubed, we can break it up to being I squared multiplied by I. And if we do I squared multiplied by I, we know the definition on the right over here, that I squared is equal to minus 1, so we can swap that for minus 1. Okay, so that's minus 1 multiplied by the I that we have left over. Minus 1 by I is equal to negative I. Dead straightforward. Now, we see we have I to the power of 13. Seems a little bit more difficult here, but what I'm going to use here is I'm going to use the second definition as much as I can. And you can see here that I know that I to the power of 4 is equal to 1. So I'm going to break this up into as many I to the power of 4s as I can. And hopefully you should be able to see that if I rewrite this out, I get I to the power of 4 multiplied by I to the power of 4 multiplied by I to the power of 4. That gets me to I to the power of 12, because 4 plus 4 plus 4 is 12. And then multiply that by another I. And you can see here now what I have is from the I to the first I to the 4, that's 1. That goes to 1. That goes to 1. And I'm left with I. So 1 times 1 times 1 times I just leaves us with I. Therefore, I to the power of 13 is equal to I. Okay, let's have a look at maybe I to the power of 22. I'll just pull that out of my hat there. So I to the power of 22, if we work that out. Then again, let's work out how many to the power of 4s we have here. Hopefully you can see, guys, we can write this as I to the power of 4 by 5, and that will get us to I to the power of 20. Remember, our index laws say that 4 times 5 is equal to 20, which means that we have an I squared left. So we've got I squared, so that's 22. Okay, so all we do then is I to the power of 4 is 1, so we've got 1 to the power of 5 multiplied by I squared, and I squared is, as we look at the definition on the right there, minus 1. So we have 1 times minus 1, which is minus 1. Okay. And that last one then, I know I put I there, but I'll put it as IV. Doesn't really make much difference. We now have I to the power of 251. So I'm going to divide 251 by 4, just to see how far we get down here. So if I do that, I do I to the power of 4, and then what I'm going to do is I'm going to calculate how many times it goes into 251. I think that's 62.75, so 62, and 0.75 means I have 3 remaining out of 4, so 62 times 4 will get me to 248, and therefore I have 3 left. Okay, we know I to the power of 4 is just 1, so 1 to the power of 62 is just 1. We can break up the I cubed now into I squared dot I. We know that I squared is equal to negative 1, so it's 1 by negative 1 by I, which is just equal to negative I. So on this slide, I suppose I'm just going to clarify exactly where the complex numbers lie with regards to our set notation. So before, what we had before was the idea of all the real numbers, but now of course we have complex numbers. So this is this big box here of complex numbers. Now we have a subset of real numbers and the q's, the integers and the natural numbers within that, and then we also have this subset of imaginary numbers, and as you can see here, the complex number lies between the two. So it's not a real, it's not an imaginary, it's a complex number, which is this box here. We can also plot complex numbers on what's called an Argand diagram, so you can see here. And this is a 2D representation of a complex number. So we have z is equal to a plus bi here. What we can do is, instead of using the x and the y notation as a Cartesian coordinate, which is what we've been doing with the real numbers, we can use, instead of the x, we have what's called the real axes, and then instead of the y, we have the imaginary axes, and then we just plot it as we would a normal xy coordinate. So here a is in the real direction, b is in the imaginary direction, which gives us a coordinate of AB. For example, if I had z was equal to 3 plus 2i, we would go 3 in the real direction, 2 in the imaginary direction, and we'd then be able to plot that. Now the modulus of a complex number, well, if you remember what modulus is, the modulus is the distance of a point from the origin. So if I have my complex number z is equal to a plus bi, there it is. So you go a in the real, b in the imaginary, just as before up here, and the modulus of z is essentially the hypotenuse of that right angled triangle that we have just created. So it's very straightforward to calculate. You can see here that z squared is equal to a squared plus b squared. That's where it is. And in order to work out the modulus, all we need to do is we need to take the square root of the a squared plus b squared, and that there is the modulus. So the modulus is the distance from the origin to where we want to get to on the Argand diagram. Right, we have an Argand diagram here, and it says there's 4 complex numbers, z1, z2, z3, and z4. And it says if one of these is 3 plus 3i, identify which one it is. Well, it shouldn't be too difficult. So if we go across, 1, 2, 3 in the real, 1, 2, 3 in the imaginary. So this one here, z2, so we can write that down. z2 must be equal to 3 plus 3i. Nice and straightforward. It then says write the other complex form. The other complex numbers in the form a plus bi. So z1. Again, shouldn't be too difficult. If you have a look at z1, you can see we've gone 0 in the real direction, and we've gone 1, 2, 3, 4 in the imaginary. So that's just going to be 4i. We have a look at z2 next, or we've done z2, sorry. If we look at z3 next, well, you can see here we've gone minus 1, minus 2 in the real. There is no movement in the I direction, so this is just a real number of minus 2, so z3 is equal to negative 2. And the last one there, guys, is that this is 1, 2, 3, so it's negative 3 and plus 2 in the I direction. So z4 is equal to negative 3 plus 2i. So just to summarise what's going on in this particular video, what we have is the complex number z is equal to a plus bi is represented by a point a, b on the Argand diagram as shown before, and the modulus is given to the square root of a squared plus b squared.